Neural networks. If you've ever wondered how machines learn to recognize patterns, make decisions, or even generate art, this is where the magic happens. They're the beating heart of modern artificial intelligence, but their story is one of setbacks, breakthroughs, and relentless curiosity. Let's explore how neural networks went from a fascinating idea to the powerhouse behind today's AI revolution. The concept of neural networks was first inspired by biology, specifically the human brain. In 1943, Warren McCulloch and Walter Pitts proposed a mathematical model of neurons, showing that networks of simple units could perform logical operations. This was a big deal. It suggested that machine brains could, in theory, mimic the way our neurons process information. But at this point, it was more of a conceptual spark than a fully realized flame. The next big leap came in 1958, when psychologist Frank Rosenblatt introduced the perceptron. The perceptron was a simple neural network designed to recognize patterns. It had a basic structure, an input layer that fed information into the network, a single processing unit that made decisions based on weighted inputs, and an output layer that delivered the result. Imagine showing it a set of images and asking it to detect whether a specific shape, like a triangle, was present. The perceptron was an early glimpse of machine learning, and it captured the public's imagination. But there was a catch. As promising as the perceptron was, it had severe limitations. In 1969, Marvin Minsky and Seymour Papert published a book that highlighted these weaknesses. They showed that perceptrons couldn't solve problems involving complex relationships, like distinguishing between connected and disconnected shapes. Essentially, if the task required more than one decision-making layer, the perceptron was out of its depth. This critique dealt a heavy blow to neural network research and contributed to the first AI winter. For a while, neural networks were seen as a dead end. But in the 1980s, something changed. Researchers began exploring the idea of multi-layered networks, systems with not just one, but multiple layers of neurons, each processing data in increasingly complex ways. This led to the development of backpropagation, a game-changing algorithm introduced by Geoffrey Hinton, David Rumelhart, and Ronald Williams in 1986. Backpropagation allowed neural networks to adjust their internal weights by comparing predictions to actual outcomes and fine-tuning themselves accordingly. With backpropagation, neural networks could finally learn from their mistakes. And this wasn't just a small step forward, it was a leap. Suddenly, tasks that had once seemed out of reach, like recognizing handwritten digits or identifying objects in images, became achievable. The introduction of backpropagation reignited interest in neural networks, but it wasn't an instant ticket to success. In the late 1980s and 1990s, neural networks were still limited by the technology of the time. Training a multi-layered network required immense computational power, and datasets large enough to be meaningful were hard to come by. The hardware and infrastructure just weren't ready yet. Still, researchers pressed on, improving algorithms and experimenting with network architectures. By the early 2000s, two key factors began to shift in favor of neural networks. First, computing power exploded, thanks to GPUs, which were originally designed for gaming but turned out to be perfect for parallel processing tasks like training deep neural networks. Second, the internet revolution provided an unprecedented amount of data. Suddenly, everything from images to text to user behavior was being digitized and collected, providing the fuel neural networks needed to thrive. This set the stage for the rise of deep learning, a branch of machine learning that uses neural networks with many layers to analyze and learn complex representations of data. Unlike the simple perceptrons of the past, deep neural networks could handle massive data sets, recognize intricate patterns, and even outperform humans in certain tasks. One of the watershed moments for deep learning came in 2012 when a team led by Geoffrey Hinton entered the ImageNet competition, a challenge to classify millions of images into categories. Their deep neural network, called AlexNet, crushed the competition, cutting the error rate nearly in half compared to previous methods. AlexNet's success shocked the AI world and proved that neural networks weren't just viable, they were the future. From there, the breakthroughs kept coming. Neural networks began driving advances in everything from speech recognition to machine translation to medical diagnostics. They could generate realistic images, detect diseases, and even create new forms of art. And with the development of transformers, a special type of neural network architecture, the field of natural language processing took off, enabling AI models to understand and generate human-like text with astonishing accuracy. But neural networks also raised new challenges. They're powerful, but they're often opaque, a black box that makes decisions without offering clear explanations. This has sparked an ongoing debate about transparency, fairness, and accountability in AI systems. As neural networks continue to shape our world, researchers are working to make them more interpretable and aligned with human values. Today, neural networks power some of the most impactful technologies on the planet. They've come a long way from the early perceptrons of the 1950s, evolving into systems that can learn, adapt, and even surprise us. Their development is a testament to the perseverance of researchers who believed in the potential of learning machines, even when the odds and the critics were stacked against them. Neural networks didn't just change AI, they redefined what machines can do. And in the process, they've changed how we see ourselves and our role in a future shared with intelligent systems.